leading astrophysicist deGrasse, Tyson and Michio Kaku have made disturbing announcements that have brought Pluto back into the spotlight. They suggested that the chilly world is on a potential collision course with Neptune, but how could this really work, and what might the outcome of such an enormous event be? Are we witnessing a bewildering, huge erraticism, or is there something else to this impending, never-ending setback? Pluto is a distant, stealthy, more modest planet that was once a part of our nearby planetary system. Join us as we examine the possible outcomes of a Pluton collision from Neptune-Pluto, a former planet that was reclassified as a dwarf planet, continues to be a topic of interest and research in the wide cosmos, as seen by recent predictions from top experts. Astrophysicists deGrasse, Tyson and Michio Kaku are warning of a potentially dangerous collision between Pluto and Neptune, which may pose a serious threat to Earth. But how is such an event even possible? Pluto's orbit is dangerously near to Neptune's. Unlike any other planet in our solar system, Pluto takes an astounding 248 years to complete one circle around the Sun, and since its discovery in 1930, it hasn't even completed one complete revolution. Nevertheless, the fascination doesn't end there. The distinctively elliptical form of Pluto's orbit distinguishes it from the almost circular orbit orbits of the other major planets. Pluto's orbit is substantially more unexpected because of its 17 degrees inclination to the ecliptic plane, which makes it far more unpredictable than other planets. This propensity and unpredictability further complicate Pluto's orbital arrangement. The fact that Pluto actually moves closer to the Sun than Neptune in each orbit, defying what we might anticipate, given their positions in the planetary system, is possibly one of the most fascinating aspects of Pluto's orbit. This raises the common question, why hasn't Pluto collided with Neptune? The answer is found in the gravitational pull of other planets. Shortly after its discovery, Pluto's orbit was examined in contrast to other planets whose orbits are relatively near to the ecliptic plane. Astronomers first tried to determine its distinct course. Pluto's orbit is notable for its irregular shape and depth. When it was discovered that Pluto's orbit did in fact overlap Neptune's, the enigma deepened. Pluto's orbit is stable in spite of these complications, demonstrating the complexity of celestial physics. The three-body problem in space concerns figuring out how three celestial bodies, such as Pluto, Neptune, and the Sun, move and affect one another through gravity. It's similar to attempting to forecast their future locations based on their starting points and the forces they exert on one another. In the case of Pluto, this problem illustrates how its orbit, the intricate relationship between the Sun's gravity and Neptune's orbit. The key to this riddle, according to astrophysicists, is non-concurrent libration, orbital precession, and Vizeke wobble for Pluto and Neptune. Non-concurrent libration is what maintains all planets in their orbits. On the one hand, this term refers to the vertical movement of a body in its orbit. For Pluto, this means that when it approaches Neptune or any other giant planet, it is positioned far above their orbital plane, adding an additional layer of protection from potential impacts. In essence, this term means that when Pluto crosses Neptune's orbit, it is positioned no less than 90 degrees away from Neptune. This spatial division is crucial in preventing their orbits from meeting. Orbital precession, the Vizeke wobbling, which is named after three researchers named Zeli and Kaku, who investigated how objects move in space, is another important factor in this scenario. It concerns how three space objects such as Pluto, Neptune, and the Sun pull on one another with their gravity, which affects how they move. In Pluto's case, despite Pluto's seemingly chaotic orbit, the Vizeke wobble helps maintain it moving smoothly over long periods of time, which helps us understand why its orbit near the Sun is so peculiar. The VZK wobble demonstrates that even though space seems to be a chaotic and unpredictable place, there are patterns and principles that keep everything under control. These forces help keep Pluto's orbit steady so it doesn't smash with Neptune or veer off course. Studying this helps us learn more about Pluto, our solar system, and even distant worlds and their stars. In the late 1980s, numerical simulations showed that despite the stabilizing properties, Pluto's orbit is actually erratic with minor deviations in initial conditions, leading to huge differences over centuries. However, these peculiarities of Pluto's orbit have been found to maintain stability over incredibly long time scales. This three-body problem is essential to understanding how these orbits change due to the way space objects pull on each other. We have gained a better understanding of how the massive planets Neptune, Jupiter, and Saturn impact Pluto's orbit around the Sun by examining the disruption from subsequent automated inspections. Neptune and Pluto have a unique connection in which Neptune completes 3 orbits around the Sun for every 2 that Pluto completes. This interaction keeps Pluto's orbit constant, but Neptune isn't the only one at work. Pluto's orbit is stabilized in large part by Jupiter's gravity. Saturn also plays a role. Research indicates that Jupiter's powerful gravity keeps Pluto on a stable course for a very long time, possibly for millions of years. So maybe Neptune, the solar system as we know, would be a much more violent place without these mechanisms. Jupiter and Saturn are working together to keep Pluto moving through space safely and without encountering any problems. Without these mechanisms, bodies like Pluto could collide with other celestial bodies or be ejected from their stable orbits, starting a chain reaction with other celestial bodies. For Pluto especially, given discussions about it possibly colliding with Neptune in the future, understanding its orbit is essential because it provides a clearer picture of the dynamic nature of the nearby planetary system. The Pluto case highlights the significance of ongoing observation and study of these phenomena to better understand our place in the universe and demonstrate how even the most seemingly unstable orbits can achieve a state of balance through the intricate interaction of gravitational forces and orbital mechanics. Investigating the depths of space often forces us to face the peculiarities of celestial bodies, and Pluto's orbit is a prime illustration of this irregularity. The concept of orbital chaos, which refers to the fragile dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can dramatically alter its long-term orbit. Using automated simulations has been hugely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on each other by tweaking small details in the simulation space. Researchers can see how even minuscule changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations showed something interesting about Pluto's orbit. Despite having features like asynchronous libration and orbital precession to keep it stable, its orbit can still be inconsistent and unusual. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. Yet, despite this chaos, Pluto's orbit remains stable over vast time scales like billions of years. This means that Pluto's journey around the Sun has a kind of order to it, even though it appears wild at first. Predicting the movement of the stars is very difficult. particularly when it involves erratic orbits like Pluto, while numerical models offer great tools for comprehending and forecasting the future movement of celestial bodies. They also highlight the limitations of our predictive abilities. This is because long-term forecasts are frequently fraught with uncertainties due to the inherent unpredictability of these systems. Apart from the chaotic nature of planetary orbits, these models rely greatly on the precision of beginning circumstances, and even a minor error or distortion may produce wildly disparate results, making accurate forecasts a difficult undertaking. Pluto serves as a reminder of the universe's dynamic and ever-changing nature. Even though we have made significant strides in our understanding of space, Pluto's case also highlights how little we still understand about the universe. Understanding the gravitational effects of the giant planets on Pluto's orbit offers important insights into the solar system's broader dynamics, demonstrating how each planet's presence and position can have a significant impact on the stability and trajectory of other bodies within the system. Therefore, why are top astrophysicists recently voicing concerns about a possible collision between Pluto and Neptune, despite all these intricate forces working to prevent such an event? Neil deGrasse Tyson, a well-known astronomer and key contributor to the advancement of cosmology, provides a distinctive viewpoint on the riddles of our solar system, particularly the fascinating case of Pluto. Tyson, who is well known for helping to change Pluto's name from planet to dwarf planet, provides perceptive commentary on how celestial mechanics are changing and how the public is becoming interested in the understudied regions of space. Tyson views Pluto's renaming as a necessary adaptation to our growing awareness of the many bodies surrounding our sun, rather than a devaluation based on our ever-increasing knowledge of our solar system. Tyson views celestial mechanics as a field that is always evolving and learning. He believes that Pluto's and other planets' intricate orbits demonstrate how much more there is to learn about space. The curiosity around these issues makes space exploration fascinating, but despite Tyson's optimism, his theories on Pluto and Neptune colliding depict a different picture. His worries about Pluto's orbit fading are based on a straightforward fact: as the solar system changes, the gravitational dynamics of objects like Pluto and Neptune might gradually change. Even while the likelihood of an instantaneous, there are very few collisions. Tyson and other experts warn that it may occur over billions of years, and that the whole system would collapse if the gravitational pull between Pluto and Neptune ever became unpredictable or unstable because of minor changes. The possibility of such a collision, though extremely rare, is a theoretical concern that highlights the fragility of celestial mechanics in our solar system. Tyson and other astrophysicists acknowledge that even though the current dynamics between Pluto and Neptune seem stable, we must take into account the long-term implications of their orbits over billions of years. Even the smallest changes in gravitational forces could alter the balance that keeps them from colliding. Neil deGrasse Tyson's remarks also highlight the larger problem of how the solar system is always changing. In the case of Pluto and Neptune, minute changes build up with each orbit and gravitational interaction. While their current orbits are synchronized to avoid direct collisions, there's always a chance that this delicate equilibrium might change over very long periods of time. Even while Pluto's orbit is currently quite stable, there is a chance that it may alter given the correct circumstances, since it crosses Neptune's orbit for a segment of each cycle. Furthermore, Pluto is subject to a long-term gravitational tug of war with not only Neptune but also other massive planets like Jupiter and Saturn. Although this influence helps to stabilize Pluto's orbit, it also means that Pluto's path is constantly moving. In this way, Pluto's orbit can be viewed as a dynamic, ever-changing puzzle where all the pieces must fit precisely for the dwarf planet to avoid any potential catastrophes. However, despite the possibility of change, it's crucial to keep in mind that as technology advances, our understanding of the solar system is still developing. Small changes to the orbits of these massive planets could shift the gravitational forces enough over millions or billions of years to push Pluto's orbit into an unstable position. Deeper understanding of the long-term stability of planetary orbits is provided by novel models and simulations. Future observations may provide further insight into the interactions of planets throughout time, improving our forecasts, and maybe even offering fresh answers to these cosmic riddles. While the idea of Pluto and Neptune colliding may seem unrealistic and unlikely in the near future, the case of Pluto and Neptune serves as a useful reminder that, despite space's apparent vastness and infiniteness, it is actually a place of constant motion, change, and unexpected possibilities. Their orbits provide an intriguing window into the dynamic character of our solar system. The delicate equilibrium in space is shown by the complex gravitational connections between planets and dwarf planets like Pluto, where even slightest changes over time may have significant consequences. As we look to the future, it is evident that the study of space will continue to be a rich area of discovery, where surprises abound. Astrophysicists like Tyson continue to investigate these mysteries, reminding us that the universe is far from static and that our knowledge of it is always expanding. There will be mysteries and fresh discoveries